Hello! In this video, we are going to prove the following theorem. For every complex number a, there exists a complex number x such that a plus x is equal to 0, and there exists a complex number y such that y plus a is equal to 0. Now in this series, we are using a list of axioms for the complex numbers. These axioms come from MetaMath, and I'll leave that list of axioms in the description below. So let's remind ourselves what we're working with. We're given a set C called the set of complex numbers. We're given a subset of the complex numbers R called the set of real numbers. We are given three elements of the complex numbers, 0, so 0, 1, and I. We're given two binary operations on the complex numbers, addition and multiplication. So given any two complex numbers a and b, a plus b is a complex number, and a times b is a complex number. We also have a relation on the set of real numbers called the less than relation. So given any two real numbers a and b, it might be the case that a is less than b. We write it like this. Otherwise, a is not less than b, and we write that. And from here, we have a list of axioms for the complex numbers. Now to prove this theorem, let's remind ourselves of the following axioms. Let's remind ourselves of axioms 1 through 7, axioms 10 and 12. I think there's a couple we won't need, but let's remind ourselves of them anyways. Axioms 1 and 2 just tell us that the sum of any two real numbers is a real number. The product of any two real numbers is a real number. Axiom 3 is the commutative law for multiplication. Axioms 4 and 5 are the associative laws for addition and multiplication. Axiom 6 is the distributive law. Axiom 7 tells us that 0 is equal to I times I plus 1. Axiom 10 tells us for every real number a, there exists a real number x such that a plus x is equal to 0. Right, so it looks kind of similar to what we're proving. Axiom 12 tells us for every complex number a, there exists a pair of real numbers x and y such that a is equal to x plus iy. Now, in proving this theorem, we are going to be using some results that we have already proven from these axioms, which are as follows. We have for every complex number a times 0 is equal to 0, 0 times a is equal to 0. We have for every complex number a times 1 is equal to a, 1 times a is equal to a. And we have proven for every complex number a plus 0 is equal to a. Okay, so now let's get into proving this theorem. So notice, we're essentially proving that every complex number has a right additive inverse and a left additive inverse. And there's nothing saying that the left additive inverse and the right additive inverse are equal. Right? We're not at that point yet. So let's get into proving this theorem. So to start out the proof, let's give ourselves an arbitrary complex number a. Now let's first prove that there exists a complex number x such that a plus x is equal to 0. So to start out, since a is a complex number, well then by axiom 12, there exists a pair of real numbers I'll call p and q, such that a is equal to p plus iq. Now to obtain a complex number x such that a plus x is equal to 0, the idea is we apply axiom 10 to the real numbers p and q. By axiom 10, since p is a real number, there exists a real number I'll call r such that p plus r is equal to 0. Similarly, since q is a real number, by axiom 10, there exists a real number I'll call s such that q plus s is equal to 0. So from experience, now it seems reasonable to claim that if we take the complex number p plus iq and add it to the complex number r plus is, it seems reasonable to conjecture that this should result in 0. Well, actually, because we don't yet know that addition is commutative, we're actually going to show that is plus r will do the work. So we're going to take x to be the complex number is plus r. We're going to show with that choice of x, we will obtain a plus x is equal to 0. So with this choice of x, we're going to show that a plus x is equal to 0. So let's substitute a for p plus iq, substitute x for is plus r. And now, applying the associative law of addition, let's move these parentheses around iq plus is plus r. And then, applying the associative law of addition again, let's move these parentheses around iq plus is. And then, by the distributive law, axiom 6, we can pull out the I, so that this parentheses just becomes I times q plus s. But then we know that q plus s is equal to 0, and we know that any complex number times 0 is 0. So we get I times 0 equals 0. Well, this is just p plus 0 plus r. Now we haven't yet proven for every complex number a, 0 plus a is equal to a. But we have proven for every complex number a plus 0 is equal to a. So what can we do here? Well, applying the associative law of addition, we can move these parentheses around p plus 0. So we have p plus 0 plus r. But now we know that p plus 0 is equal to p, because we've proven for every complex number a plus 0 is equal to a. So p plus 0 is equal to p. So we get p plus r, and then p plus r is equal to 0. So this shows that a plus x results in 0. So this choice of x works. We have shown that there exists a complex number x such that a plus x is equal to 0. So we have proven 1. Now for 2, the trick is to use axiom 7, which says that 0 is equal to II plus 1. What we're going to do is we're going to take y to be a times II. So now let's show that y plus a is equal to 0. Well, let's substitute y for a times II. We know for every complex number a times 1 is equal to a. So we can replace the a here with a times 1. And then applying the distributive law, we can pull out the a, so that this is just a times II plus 1. But then we know from axiom 7 that II plus 1 is equal to 0. So this is just a times 0. But we know any complex number times 0 gives us 0. So this is just 0. So y plus a is equal to 0. And so our choice of y works. We have shown that there exists a complex number y such that y plus a is equal to 0. So we've proven 2. So this completes the proof. And so yeah, that's pretty much it for this video.